So now we're going to look at antiderivatives. Antiderivatives are basically going the other way. When we have a function and we take the derivative, now we're starting with the derivative and we're going back to what the original function was. So if we have, well, in terms of notation, if we have a capital F of x, which is an antiderivative of little f of x on some interval, we can then say that if we take the derivative of the capital F of x, that should equal then the little f of x for all a and b, for all x inside the interval a, b. Now, the one thing we have to consider is that when we have an original function, if we ever have a constant and we take the derivative of a constant, it becomes 0. So when we're taking an antiderivative and we're finding the antiderivative, we have to keep in mind that in general, if we're going backwards and we don't know what that constant was, we have to have some constant c represented. Another thing that we also need to know is the new notation. So the key thing here is that we have our new notation for an interval, or integral. We now have integral notation. So if we take the integral of our function, we should get our capital F of x plus some constant. Because if we were to take the derivative of this, this would then give us the f prime of x, and the c would then just become 0. So now the f of x plus c is now just referred to as your general antiderivative, or the indefinite integral of f of x. Indefinite because we don't know what c is, but we know there is some constant there. So now we're going to look at just a basic example, one that you probably have worked with before. If I give you the function f of x equals 1 over 2 root x, and they want to know what the antiderivative is. This one we know from many examples. We basically have done this one over and over and over again. What did we actually start with in order to get the 1 over 2 root x? Well, we know that the square root of x, just from our experience, is going to be the antiderivative. But again, we don't know exactly if there is a constant or not, so we add in a constant. So if we were to take the integral of 1 over 2 root x, we would write it as root x plus c. We can check to make sure it makes sense. If we take the derivative of this, we would then have the derivative of the root x plus the derivative of c. Then we know that this one, using the power rule, becomes 1 over 2 root x, and this guy here becomes 0. So yeah, that would work. So just like with the derivative, we now have some rules that will help us. So the power rule for integrals, when we're working with derivatives, when we take the derivative, the degree goes down. When we do an integral, the degree should go up. So as you notice, if we have the integral of x to the n, then we have to go up a degree and divide by the power, raised up to 1 power. So if I look at the first example and I see that we have a power of 3, I'm going to have x to the 4, so I go up a degree, and I'm going to divide by 4. Again, you can check. If I take the derivative with respect to x of x to the 4 over 4, that's going to give me, bring the 4 in front, x to the 3 all over 4. The 4's will cancel out. That leaves me x to the 3. But again, we don't know if it actually had something more to it, a constant. Because technically I could have had something like this, and then this portion here, when I take the derivative, becomes 0. So again, we need to have this plus c. So another example here, if I have the integral of x to the 6, then I need to go up a degree, divide by 7, plus c. Two more rules also that kind of make sense based on our derivative rules are our sum rule and our multiples rule. The sum rule is also the sum and difference. You could technically say plus or minus, plus or minus. It doesn't really matter what sign's in between as long as there's a sum of either two positives or a sum of a negative. When you're working with the sum rule, you can split it up into parts. And when you have a constant, you can move the constant out front. So if you had an example like this that was a little bit more complicated, if we just use our multiples rule first, we can move our constants out, and if we break it into all the parts, constant go out front, and then we have all our terms. So the multiples rule brings the 3 out front, the 2 out front, and the negative 4 out front, and our sum and difference rule splits them into the parts. From that point, we can then take the integral. So to do that, we'll start with the 3 out front. We have x to the 4th. We want to go up a degree. So x to the 5 all over 5 plus 2. And again, we have negative 2, so we want to go up by 1. So we want to go x to the negative 1 all divided by negative 1. Subtract 4. And here we've got 3 over 2. I want to go up 1, which makes it 5 over 2. All divided by 5 over 2. So then we can simplify this down. 3/5 x to the 5th. This will make it minus 2 x to the negative 1. And then here, keep in mind when you have a fraction, you're dividing by a fraction is the same thing as multiplying by its reciprocal. So then we would have that multiplied by 4. So we would have minus 8 x to the 5 over 2 all over 5. And of course, because we're doing an integral, plus c. Don't forget. So because we know all the trig identities when we take the derivative, now we can also look at all the basic trig integrals as well. So, more or less, if we were to take the derivative of cosine, you would get negative sine. So, if I switch to sine, if I take the derivative of negative cosine, you're going to get positive sine. If I take the derivative of sine, you'll get cos. If I take the derivative of tan, you'll get secant squared. If I take the derivative of cotangent, I get negative cosecant squared. So if I have a negative cotangent, that'll make it a positive. If I take the derivative of secant x, I'll get secant x tan x. And if I take the derivative of cosecant x, I'll get negative cosecant cotangent. So again, opposite signs. So this is something that you should know. Definitely these two here. Just like when we do the derivatives, you need to know those two. The other four will be provided. And what we've looked at so far are general antiderivatives, where they have a constant c that have been added to it, which means there's technically infinitely many possibilities for c. So there's infinitely many possibilities for the antiderivative. Some of the problems you'll see will actually involve initial value problems. They want you to solve this statement here subject to an initial condition. In this case, the initial condition is that the function has an input of 0 and an output of 5. So in order to do this, you start with the dy dx equals to 3x to the 9. One way to think about this is that you can move your dx over to this side, and then you'll take the integral of both sides. So the integral of dy equals to the integral of 3x to the 9 dx. This, an integral of a derivative, just gives you back to the original, so your y. And then this one here we can work with, again, all our rules that we've been working with. So it's 3 integral of x to the 9 dx. Then we can go up a degree and divide by that value. So y is going to equal 3 x to the 10 all over 10 plus c. Now what we have now is an initial condition. The initial condition tells us that when we plug in 0 into our original function, we get a value of 5. So if we use this function that we just came up with, and we plug in 0, we'll get 0 to the 10, which just becomes 0, all over 10 plus c. This part disappears, equals c. Therefore, c is going to equal to 5 in this particular case. If I gave you an initial condition of 1, then you'd have to figure out what value it would be by plugging a 1 in to the power of 10 all over 10 times by 3 and solve for c. So our actual function in this particular case is going to be 3x to the 10 all over 10 plus 5. It solves for the value of c.